Hello everyone, welcome back to our lecture video. This time let's tackle first law of thermodynamics. In mechanics, work done in moving an object like this in our illustration. So the work done in moving an object depends only on the initial and final positions. So this is basically the concept of potential energy. So either you lift the stone straight up from 3-meter height, or you will use the 6-meter ramp to lift the stone to the same elevation. So the potential energy depends on the initial and final position. Let me write the principle in here. Potential energy, the initial and final positions. However, in thermodynamics, in here in our illustration, when our system change from initial equilibrium state to final equilibrium state, this affects the system's internal energy, or U. U is the symbol for internal energy. Okay. So since Q is the heat transferred as a result of temperature change, and W is the work done on or by the system, then the Q minus W can represent the change in internal energy, or mathematically, delta U is just equal to Q minus W. Okay, this follows the conservation of energy principle, or this equation is our first law of thermodynamics. First law of thermodynamics applies the principle of conservation of energy. Conservation of energy principle. That in an isolated system, the total amount of energy is constant. Total energy is constant. That energy cannot be created nor destroyed, but it only changes forms. So in here, the energy entered minus energy left is equal to the change in energy within the system. So, from this equation, it is obvious to see that the heat supplied, in our illustration, the heat supplied into the system was used to change the internal energy of the system, and also in pushing the piston up in performing the work. So we can use this equation, first law of thermodynamics, in different thermodynamic processes. So let's consider the first thermodynamic process, the isochoric process. In this process, this is known as the constant volume process. So in this kind of thermodynamic process, no work is done on or by the system. Why? Because there is no compression or expansion in this type of process. Okay, as we can see that work in our previous lecture video, work is equal to P delta V, or pressure times the volume final minus volume initial. So since there is no compression or expansion, this quantity is equal to 0. Therefore, work is equal to 0. Our first law, or first law of thermodynamic equations, becomes Q minus W is just equal to delta U. If work is 0, then Q is simply delta U. Or Q is equal to UF, internal energy final, minus internal energy initial. So in this case, all heat is used to increase or decrease the internal energy of our system. So example to this process, it's the rise in pressure and temperature produced by the transfer of heat into the substance in an expanding container. Okay, we can also illustrate our isochoric process using the PV diagram. Okay, in our isochoric PV diagram, we have in here the red arrow. This one represents the isochoric process, wherein the initial, the tail of this arrow, and the final state of the thermodynamic process has constant volume. Okay, another process is the isobaric process. So this is a constant pressure process. So in this case, there is no automatic zero value. So there is no automatic zero value in this thermodynamic equation. So our equation, delta U is equal to Q minus W. So however, since in this case, pressure is constant, P is constant, so therefore we can solve for work done. We can solve for the work done since P is equal to VF minus volume final minus volume initial. So we can solve for the work in here. So the typical example for this process is when water enters the boiler of steam engine as our system and then heated to its boiling point and then vaporized. So this is a typical example for an isobaric process. Again, let's illustrate using a graph. So the isobaric PV graph. So where's the isobaric in here? So if this is our initial state and our final state as pointed by the arrow, we can see that the pressure is constant. Okay, another process is adiabatic process. In here, adiabatic process meaning heat Q is equal to 0. So in this process, no heat enters or leaves a system. So this can be accomplished either you surround the system in here with excellent heat insulator, or you can perform the thermodynamic process quickly, meaning that the time interval between the initial and final equilibrium state is very short, thus allowing no heat to flow. So what will happen to our equation now? Since Q is 0, our delta U is, okay, from first law, delta U is equal to Q minus W. If Q is 0, then we have delta U equal to negative W. Our UF minus UI is equal to negative W. So example to this kind of process is the mixture of gasoline vapor and air during compression stroke of a gasoline engine. So showing the graph of our adiabatic process, so it looks like this, represented by the green line. Okay, that's our adiabatic PV graph. And then isothermal process. So in this process, temperature remains constant. So T is constant. In our adiabatic process, heat is 0. But in isothermal, heat is not 0. So meaning there is transfer of heat energy just enough to keep the same temperature. The transformation is slow, unlike adiabatic that may require a quick process. Basically, the difference of isothermal process and adiabatic process. The isothermal or isothermic process, PV or pressure volume graph, is or can be illustrated in this manner. So we have PV equals constant pressure volume graph, and then the relationship with pressure and volume is represented by this green line. Let's tackle sample problems in our next video.